Boom. All right, ladies and gentlemen, welcome. This is the voice of Dr. Joliban. Oh, yes. Introduction. My name is Joliban, doctor to be precise, a doctor of philosophy in electrical electronics technology. And I'm going to be your online presenter. And in today's video, we are going to be discussing Physics 104. Yeah, General Physics 104, aka waves, optics, and vibration, right? So the general textbook you're going to be making use of for this course is actually wave optics or wave vibrations and optics, as the case may be. So it is a single textbook that is made up of 12 chapters. And in those 12 chapters, you're expected to answer questions in all the 12 chapters. Okay, so you are not choosing some chapters and leaving other chapters away. So Physics 104 actually is not offered by all departments. You just got to find out your department if your department offers this course. So, but if you're in engineering, you offer it. If you're in physical sciences, you do. School of Medicine, you do. Basic medical science, you do. Agric, you do. So you just have to find out the course area you are. If you are not above the mentioned one, then you have to find out if you really offer this course. So, but however, it is a 2-credit loaded course and it is made up of 12 chapters. Chapter 1 is vibrations. Chapter 2 is damp oscillation. Chapter 3 is force damped harmonic oscillation. Chapter 4 is waves. Chapter 5 is interference of waves. Chapter 6 is normal mode. Chapter 7 is optics. Chapter 8 is reflection on plane surfaces. Chapter 9, refraction through plane surfaces. Chapter 10, refraction through curved surfaces. Chapter 11, optical instrument. And finally, chapter 12, dispersion and aberration, right? So basically, these are all the chapters you're going to see as far as this course is concerned. However, we are going to be kicking off with chapter 7, which is optics, okay? So after optics, we go through the concept of waves, damp, waves, vibrations, and all that. Okay, so very quickly, let's get started. What is optics? Optics is simply the study of light and vision, which is very important to every living organism, okay? Very, very important. Now, the aim of this chapter is to simply explain the phenomenon or the phenomena that involves reflection and refraction, to know how they are applicable in everyday by day life experience. For example, formation of rainbows, formation of mirage, the spectrum of colors that are formed in glass prisms, and many other stuffs like that. So optics is divided into 2 broad topics, okay? 2 broad topics, you find them there. The first part of it is the physical optics, while the second part is the geometric optics, okay? So we start with physical optics. What is physical optics? From the word physical, what is physical optics? Physical optics simply involves the study of those properties of light that cannot be explained by the use of rays, okay? The study of light that cannot be explained by the use of rays, rather by the use of waves. For example, formation of rainbow. This is not as a result of rays, but as a result of wave, okay? So, but when you want to discuss things that has to do with rays like reflection, refraction, then you think about geometric optics, okay? Geometric optics involves the use of straight lines and angles to investigate optical properties. For example, reflection, angle of reflection, angle of refraction, stuff like that. Incident ray, refracted ray, normal, blah, 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 blah. So when you talk about geometric optics, you're talking about angles, you're talking about lines, you're talking about geometry in mathematics in total, okay? So but when you talk about physical optics, you're talking about the study of physics that don't look at things as rays, but look at things as waves. Wow. What is a ray? A ray is simply the direction or path taken by a wave. Mind you, a ray is the direction or path taken by a wave of light. There are, however, 5 basic facts about a ray of light. Number 1, it points in the direction of flow of energy of the wave. Oh yes, that's the gospel truth. Number 2, a ray of light has its radius, or let me put it in this way, it is the radius of a spherical wavefront. In other words, the ray of light shows the radius of a spherical wavefront. Then number 3, it travels in straight lines and are always perpendicular to the wavefront. Rays always travel in straight line and they are perpendicular to the wavefront. Rays also travel through different media in straight lines. That's the fourth one. They travel through different media in straight lines, even though the speed and the direction of the wave will change. What happens? They change along in straight lines. Waves do not bend. What I mean by bending is taking a sharp curve. No, if it must change direction, it does that in straight lines. That's a fact. Then the fifth one will say that when a ray of light is incident to a translucent material, three things are bound to happen. Number one, the ray of light is partly reflected, and that is R. Number two, the ray of light is partly transmitted through the material, that's T. And then number three, the ray of light is partly absorbed by the translucent material, and that is A. Now look at this diagram. If you check very well, I there signifies the incident ray, R is a refracted ray, A is the absorbed ray, and then T is a transmitted ray, right? So the gospel truth about it is that the incident ray is equal to the reflected ray, the transmitted ray, and the absorbed ray. So that is why you see I equals to RTA, right? That's the algebraic sum of RTA now. So that takes us to the different types of rays. How many types of rays do we have? Basically two in number. Number one is a paraxial ray, while number two is the marginal rays. What are paraxial rays? From the word paraxial, well, we will have to involve them with principal axis. That's the gospel truth. Paraxial rays are simply those rays that are very close to the principal axis of curved mirrors and even lenses. They travel parallel or almost parallel to the principal axis and form very small angles, right? You call them paraxial rays. While marginal rays are those rays that are far away from the principal axis and are not parallel to it at all. A typical example are radial rays or focal rays, as the case may be. So that is that for the different types of rays. That takes us to beam. What is a beam? A beam of light is simply the collection of light rays. If you have a single ray of light, it can never form a beam. But if there are two, that becomes a beam, right? Or three, as the case may be. Now, we also have different types of beams, and basically two types. Number one, we have the regular beam, and we also have the scattered beam. Regular beams are formed by smooth surfaces, while scattered beams are formed by rough surfaces. Regular beams are also called, which word do I use now? They are also called specular beams, while scattered rays are also called diffused beam. Regular rays do get themselves reflected at specific angles. Regular beams, specific angles of reflection, 60, 60, 60, 60, 60, all through. As for diffuse or scattered beam, they get themselves reflected haphazardly. In other words, there is no specific angle of reflection. That's the basic difference between the two of them. So look at these two diagrams. You have the regular or the specular beam, and here you have the diffuse and the scattered beam. You see how haphazard it looks like. That takes us to reflection. What is reflection? Reflection is simply the returning of a ray of light when it hits a medium. It can also be referred to as the absorption and the re-emission of light when it strikes a surface. This surface can either be smooth or rough surface. When it strikes a smooth surface, it's referred to as regular reflection. When it strikes a rough surface, it is referred to as diffuse or irregular reflection, right? So those are the two types of reflection. Number one, regular reflection. Of course, just like we did in beam, regular reflections are also called specular reflection, and they take place in smooth surfaces and they are regularly reflected, right? While when you talk about the concept of irregular reflection, you must remember a rough surface, and then you must have the ray of light haphazardly reflected. Very, very important. Now, it is important for you to know that since there is no surface in this world that can be microscopically defined as smooth, you understand the meaning of the word microscopically defined as smooth? In other words, that surface you are calling smooth now, if I zoom or see it through a microscope or an electron microscope, for example, it will appear rough. So there is no surface that is microscopically defined as being smooth. However, physics now draws a line here. When a particular surface, I repeat, when a particular surface is defined smooth, it simply means that that surface has its own. Sorry for that call. I had a call, so I went off. So back to what we're saying. A surface is defined microscopically smooth if and only if the surface irregularities of that surface is equal to the wavelength of the light incident on that surface. Then you can define it as being microscopically smooth. What do we mean? If, for example, the incident ray of light on a particular surface is 10 nanometers, right? Now, that's the wavelength of that light now. What we are saying is that if the wavelength of the light is 10 nanometers and the surface irregularities that it is coming in contact with is also 10 nanometers, then you can define that surface as being microscopically smooth, right? And then also it is important for you to remember that that different reflection, or let me put it this way, diffuse reflection is one of the reasons why illuminated objects can be seen. Diffuse reflection. For example, the moon. The moon is an illuminated object. You can see the moon because of the concept of diffuse reflection, scattered reflection, haphazard reflection. Okay? But smooth surfaces, on a normal day, you can't see a smooth surface, bro. You may wonder how. Let me ask you a simple question. Can you see the surface of a mirror, like directly 90 degrees to the mirror, and you tell me you can see the surface of a mirror that is assumed microscopically smooth? You can, bro. You can. What you're seeing there is a reflection of yourself or the reflection of the environment around you. Why? Because the reflection that is taking place is smooth, is orderly, is copacetic, so you can't see the surface. If it was haphazard, then you will see the surface. If I can see you, it's not because you are smooth. It's not because your face is smooth. It's not because your face undergoes smooth reflection. No, it's because it undergoes haphazard reflection. That is why I can see you. If it was regular, you appear transparent. All right, that's by the way. That takes us to the facts of reflection. There are basically 3 facts you must know about the concept of reflection. Number 1, during reflection, energy is totally conserved and not the amplitude. Exam question. During reflection, energy is totally conserved. The energy at the point of incident is equal to the energy at the point of reflection or refraction, as the case may be. No energy is lost. Conservation of energy, not amplitude. Number 2, during reflection, especially when light rays move from a less dense medium to a denser medium, maybe from air to water, there is a phase change of 180 degrees or pi. Very important. Phase change from a less dense to a dense medium. Then number 3, for a boundary that is infinitely massive, total internal reflection occurs since there is no room for refraction or transmission. Why? Because the boundary is infinitely massive. I mean, how can transmission or refraction take place in such a boundary? So total internal reflection is bound to occur. And now that takes us to the laws of reflection. There are basically 2 laws of reflection. Law number 1, the reflected ray, or let me put it this way, the angle of incidence is equal to the angle of refraction. And that is theta I being equal to theta R, right? And then number 2, the incident ray, the reflected ray, and the normal at the point of incident all lies on the same plane. You did that in O level, right? You remember? Good. What you're doing here is simply applied version of what you did in O level. And if you look at this diagram, you see the incident ray, the reflected ray, you see the normal, theta I is equal to theta R, right? Now, there is what we also call the glancing angle, which you will not see in your textbook. Glancing angle is simply the angle formed between the mirror and the angle of incidence, okay? So, and that is represented by G. And the gospel truth about it is that the angle of incidence is equal to the angle of reflection. And since they are equal, then the angle between the mirror and the incident ray is also equal to the angle between the reflected ray and the mirror. And then on that note, you can calculate the deviation of the ray of light. And if you look that very well, applying the laws of geometry, the angle of deviation by the incident ray that got reflected is 2 times the glancing angle. That takes us to the concept of refraction. What is refraction? Refraction is simply the change in the direction of a ray when it travels through a medium of different densities. Their densities must be different. If they are not different, then there is no refraction. Okay? And there are basically 2 facts you must know about refraction. During refraction, that's the first fact. During refraction, some of the energies, let me use the word energies in quotes, some of the energies is not refracted now, but reflected. Okay? While some are being transmitted. The transmitted ones are refracted. Okay? So during refraction, some energies are being reflected while others are being transmitted. And the direction of transmission is always different from the direction of incidence. Right? That's number 1. Then number 2, also during refraction, it is important for you to know that there is a change in the wavelength or the speed of the light or the waves that is in motion, but the frequency remains unchanged. Never will the frequency change during refraction. Take note, exam question. Frequency is always kept constant because every ray has its own frequency, and that frequency is applied irrespective of the medium of transmission. Take that ray in a vacuum, that is the frequency. Take that ray in water, that is the frequency. It does not change. The only thing that changes is wavelength. Right? So that takes us to the laws of refraction. There are basically 2 laws of refraction as well. And the very first law of refraction will tell you that the incident ray, the refracted ray, and the normal at the point of incident all lies on the same plane. Where the second law, being called Snell's law, states that the ratio of the sine of the angle of incident, theta I, to that of the sine of the angle of refraction, theta R, is what? Is inversely proportional to the refractive index of the 2 media. And this is called Snell's law. And then you have sine theta I all over sine theta R being inversely proportional to A and B. That A and B you see is read as the refractive index of A to B. Or you can actually call it the refractive index of A through B. You get it? Now, the N there simply refers to as a refractive index. And of course, the refractive index of A to B is also equal to the refractive index of A all over the refractive index of B. And when you substitute that in that formula, you will end up with the refractive index of A times the sine of the angle of incident is equal to the refractive index of medium B times the sine of the angle of refraction. And because it is an inverse proportionality, you can use 1 and 2 to represent the 2 media, okay? So the refractive index of medium 1 to the sine of the angle of medium 1 is equal to the refractive index of medium 2 to the sine of the angle of medium 2. That is an inverse proportionality. Refractive index, refractive index, refractive index. What is refractive index? That's a big question. Refractive index is simply the comparison of the speed of light in a vacuum to the speed of light in any material medium you can imagine. If you dare compare the speed of light in a vacuum to that of maybe water, oil, glass, or anything at all, that is refractive index, okay? Let's assume the speed of light in a vacuum is 3 million meters per second. This is not an assumption, it's a fact. That's 3 times 10 raised to the power 8 meters per second. That's the speed of light in a vacuum. Now, and the speed of light in maybe water, for example, let's assume is maybe 2 times 10 raised to the power 8 meters per second. By the time I find the ratio of the speed of light in a vacuum to the speed of light in water, that will give me the refractive index of water. And if I do that with respect to glass, I will get the refractive index of glass. If I do that with respect to oil, I will get the refractive index of oil. And through so many calculations and experiments, it has been found that the refractive index of water is 1.33, while the refractive index of glass is 1.5. The refractive index of air is 1. And the refractive index of flint glass is 1.44. The refractive index of crown glass is 1.38. And it continues like that. The list is just endless. Nota bene. Nota bene. Refractive index at times depends on the wavelength of the light, but totally independent of the frequency. In fact, not even at times, all the time. Refractive index only depends on wavelength, irrespective of frequency. And that is why from the formula n equals to CV, C is the speed of light in a vacuum, while V is the speed of light in any medium. And we already know that V is equal to F lambda. Lambda is the wavelength of the medium, F lambda M. And C is also F lambda, right? So if you substitute that in that formula, you will discover that F will cancel out because the same frequency is applied. So the refractive index becomes the refractive, the wavelength in a vacuum all over the wavelength in a medium. And that is why you say lambda all over lambda M. So that is refractive index. And in that formula, you have no business with frequency. So refractive index is independent of frequency, but highly dependent of wavelength. So that takes us to the relationships in refractive index. Let me assume you have three media, medium A, medium B, medium C, just like you see in this diagram. The angle of incidence of medium A is theta A. The angle of refraction is theta B. That theta B, yeah, while if you go to the second medium, theta B, theta C, you go to the third medium, theta C and theta A. Right? Now, at the first medium, the refractive index of A to B is equal to sine theta A all over sine theta B. As for medium B, is sine theta B all over sine theta C. As for medium C, is sine theta C all over sine theta B all over sine theta C. Right? Now, but it's important for you to know that when you multiply these refractive indexes, or indices, no longer indexes, that's wrong English. When you multiply these refractive indices, what you're going to have at the end of the day is the refractive index of A to B times that of B to C times that of C to A is equal to a unity, which is 1. And if you doubt it, substitute the signs. You have sine theta A all over sine theta B, sine theta B all over sine theta C all over sine theta A, everything cancel out and you have 1. And on this note, the refractive index of A to B times the refractive index of B to C is simply equal to the reciprocal of the refractive index of C to A, or simply put, the refractive index of A to C. You get it? So you have the refractive index of A to B times the refractive index of B to C equals to the refractive index of A to C. A lot of exam questions are centered in this relationship. So don't mess around with it. Get it right and get ready for exam. And that takes us to the last part of today's work, which is total internal reflection. What is total internal reflection? This is a phenomenon in optics that occurs when a ray of light travels from a dense medium to an optically less dense medium. And when the angle of incidence in this travel happens to be continually increased, there comes a point where the refracted ray formed turns to become 90 degrees to the normal. Now at that point, no more ray can experience refraction. Now that angle at which no ray can further experience refraction is referred to as critical angle, theta C, critical angle. However, if you dare exceed this critical angle by increasing the angle of incidence by just 1 degree, the ray will now be totally internally reflected. And that is what is called total internal reflection. So on a nutshell, for total internal reflection to take place, 2 conditions must be fulfilled. Number 1, the ray must travel from a dense medium to a relatively less dense medium. Then number 2, the critical angle must be exceeded. Now take note, there is always a contradiction between critical angle and the angle of incidence. The angle of incidence is never the critical angle. The critical angle is actually the angle of refraction formed by the angle of incidence. The angle of incidence is the critical angle, while the 90 degrees formed by the refracted ray is referred to as the angle, what am I trying to say again? I think I'm messing it up now, but I believe you understand what I mean, right? If you don't get it, forget about it. All right, now look at these 3 diagrams on the screen. First, you have a ray of light moving from a denser medium to a less dense medium, theta and theta r, you see, that was normally refracted, right? Now it's refracted away from the normal because it is a length dense medium. Now in the second diagram, you discover that the critical angle has been increased, and now the ray is now perpendicular to the normal. So if you check, the angle of refraction is now 90 degrees, right? Now this is the critical point. Why is it critical? Because if you dare increase the angle of incident by 1, it will hit totally inside the same medium, and that is reflection. And that is what happens in the third diagram. The angle of critical is being exceeded, and the ray now turns back on the same medium, and that is total internal reflection. How can you find total internal reflection applicable in other surfaces or other stuffs? Number one, you find it applicable in optical fibers to see across obstacles and even across bends. You can also find the concept of total internal reflection applied in mirage, formation of mirage, okay? And also helping fish to have a wide range of view inside water. They make use of the concept of total internal reflection. Wow, congratulations. You made it. This is about 25 minutes and you have been listening and watching this video and you made it this long. If you have not clicked that like button, do well to click that. And trust me, you have gathered a lot as far as this chapter is concerned. You did that in 25 minutes, what is done in class for about 3-4 hours, right? So if you have not subscribed to our channel, please do well to do the subscription. Share this video with your friends, and trust me, you're going to do them more good than harm, because they're going to learn and make physics appear very simple, right? So if you do not mind, you can always join us at our live classes at Quintessence Tutorials. We meet virtually every day, Monday to Fridays, usually between the hours of 2 p.m. to 5 p.m. Okay, just 3 hours. Come around and we'll show you a lot of things. This video I'm going to show you right now will give you directions of how to get to Quintessence. Thanks for watching. Do have a lovely weekend. Boom.